Here we are going to look at Le Chatelier's principle and how do reactions at equilibrium respond to a disturbance or a stress. Many reactions can be reversible. The reactants form products and the products can form back into reactants. When the rate of the forward and reverse reactions are equal, the reaction has reached equilibrium. So the speed of the forward reaction is equal to the speed or rate of the reverse reaction. The reaction, however, does not stop, but the concentration of each chemical stays constant. This is known as dynamic equilibrium. We've looked at this so far in your first section of the book, and we've seen that dynamic equilibrium, when we look at it from a macroscopic view with what our eyes can see on their own, it doesn't look like anything's changing. However, if we could zoom into the microscopic view, we would be able to see that the reactants and products are going through their reactions and they're just happening at the same rate. So that's why it's called a dynamic equilibrium. There's still something happening at that microscopic level. We just don't see it in the macroscopic view. The first way we can change a reaction and shift its equilibrium is through the concentration of our chemicals. When the concentration or amount of a chemical is increased, the reaction equilibrium shifts away from that chemical towards the opposite side. So an example of this would be in this reaction seen below. If I added more nitrogen gas to my container, so the whole reaction is in one container, if I add more nitrogen gas to that, that's extra reactant. So the forward reaction will take over and it will shift to the right towards the products. When that shift occurs, we are going to use up some of the hydrogen, so its amount will decrease, and we're going to be making some of the ammonia, so its amount will increase once the equilibrium is reestablished. It says when the concentration or amount of a chemical is decreased, the reaction will shift toward that chemical to the same side. So say we looked at hydrogen. If we decrease the amount of hydrogen and took some of it out of the container or had less of it, then the reaction would shift towards the hydrogen because the reverse reaction would need to take over and make more hydrogen to replace what was removed. In doing this, we would increase our amount of nitrogen because we're going to make more of those reactants, and we would use up some of our ammonia, NH3. So its amount would decrease once the equilibrium is reestablished. So adding a chemical shifts it towards the opposite side, and removing a chemical shifts the reaction towards the same side that that chemical is on. Another way that we can shift a reaction or cause a stress on a reaction is when heat is added. So we do that through temperature, seeing an increase in temperature. The reaction will shift away from the heat towards the opposite side. So this follows the same situation as changing the concentration. So in our reaction below, our heat is on the right side. It's an exothermic reaction, so delta H would be negative. So if it's written separately, we would have that. So if we add more heat, then it's like we have more product. It will shift the reaction to the left. So we will make more reactants, we'll get more nitrogen and more hydrogen, those amounts will increase, and we'll use up some of the ammonia to cause that shift. So once equilibrium is reestablished, adding that extra heat causes nitrogen and hydrogen to form and ammonia to be used up. If we decreased our amount of heat, heat is removed, the reaction will shift towards that heat to the same side. So we want to reform what we've used. So in that case, we would have to use up our nitrogen and hydrogen and make more ammonia, and in that case, make more heat or energy to replace what we took away. Okay, so we could do this. If we wanted to remove heat, we would put it in an ice bath, maybe, for the reaction. If we wanted to increase, we might have it over a hot plate or have it over a flame and add energy in one of those ways. The next way we can change the equilibrium of a reaction is by changing pressure. So water placed in a vacuum chamber in a beaker can be made to boil in a vacuum chamber. So by only changing the pressure, we can boil water. We're not changing the temperature. So that's kind of an interesting situation that most people aren't used to. I'll add a link in the description of this video for you to see what that looks like. So when pressure is removed through a vacuum chamber, we're removing the air from around the container and everything. We're removing that extra air pressure, the water can boil. So this change we can write as a little reaction. So when we remove pressure, when pressure goes down, it shifts the reaction towards our gas. Okay, shifts to the right to make more moles of gas. So when pressure goes down, it's basically another way to increase our volume of our substance or our reaction, and so we want to make more gas. Okay, so we're going to shift to the side with more moles of gas. Well, on the left side we only have liquid, on the right side we only have gas, so we're going to shift to the side with more gas. So when pressure is decreased, the volume is going to increase for this situation. So if pressure goes down, volume goes up. Just like we learned in our gas laws, they are opposites of each other. So the equilibrium will shift toward the side with more moles of gas. Okay. When pressure is increased, P goes up, then volume decreases. Again, they're opposites. The equilibrium will shift to the side with less moles of gas. So we find the number of moles of gas by totaling the coefficients for the gases on each side of the balanced reaction. So we have 1 mole of nitrogen and 3 moles of hydrogen in this reaction on the left. So that gives us 4 moles of gas on the left. And then we have 2 moles of ammonia on the right, so 2 moles of gas on the right. Again, looking only at gases because pressure doesn't affect solids or liquids or aqueous solutions. So if pressure is increasing pressure would shift the reaction. So pressure is increased, it's going to shift the reaction to the side with less moles. In this case, it would shift it to the right because we have less moles of total gas. So when we increase the pressure, we're kind of pushing all those particles together. We're decreasing that volume. So if we have less space, we want less particles. Okay, less space, less particles. I'm going to put that on here. So we want to shift to the side with less moles of gas, okay, towards the right in this case. Decreasing our pressure, as we saw in the first little bullet point, is going to shift to the side with more moles. So if we decrease our pressure, we increase that volume, we spread it out, we want to fill up that space. So if we have more space, we want more particles. So we're going to shift towards the left. Decreasing the pressure would shift this reaction to the left. So if we had equal moles of gas, then no shift would occur. Okay, pressure would have no effect on the reaction if we had equal moles of gas, because increasing or decreasing that pressure, there's no side to force the reaction towards, so we would see no change in equilibrium in our position. All right, catalysts and solids can pop up here, so let's see what happens with them. A catalyst, as we know from our last unit, will speed up the rate that the chemical reaction occurs. However, the reaction will still reach the same equilibrium and have the same concentrations of each chemical. It will just get there faster. So catalysts have no effect on the final equilibrium or the concentrations at equilibrium. If a question asks what would a catalyst do to the equilibrium, it would have no effect. Same thing goes with surface area of our solid. So we saw in class and in our lab that if we increase the surface area, we break a chemical down into smaller pieces, the reaction speeds up. Again, it does not change our equilibrium. The chemicals just get to equilibrium faster. So those things would have no effect on the equilibrium itself. So let's try this out a little bit. So for each, we're going to determine the direction of the shift. Will it shift left or right, or not at all? And determine if each chemical will increase or decrease their concentration after the equilibrium is reached. Okay. So you'll see some of them are X'd out. That's because that is the chemical that's already being described, so we don't have to analyze that one on top of that. So let's take a look at our first one. If we add water, so water is a product, if we increase that amount of product, predict which way it will shift. Hopefully you said towards the left. So that will increase our amount of reactants. So we'll have more hydrochloric acid and more oxygen gas. And we will use up some of the chlorine in that process. So adding more water will cause that chlorine to get used up to form the HCl and the O2. All right, in our next one, adding HCl, that reactant, has the opposite effect. So we're adding to the left side, so it's going to shift right. So the added HCl will react with O2, so we'll lose some of our O2, but we're going to make H2O and Cl2, so we're going to increase their concentrations. All right, our third one, removing oxygen. So take a minute, think about that one. So we remove that oxygen, we have this space we need to kind of get back, right? We need to reform the oxygen. So it's going to go towards that oxygen. By having the reverse reaction take over, we're going to make more of the HCl and more of that oxygen that we removed. And we're going to use up and lower the concentrations of the water and the chlorine gas. Now our last one here is increasing pressure. So to look at that, we need to, again, look at our total moles of gas on each side. So on the left side, we have HCl as aqueous, so we ignore that. We have O2 gas, so we have 1 mole of gas on the left. On the right, we have water as a liquid and 2 moles of chlorine gas. So we have a total of 1 mole and 2 moles. So if we increase pressure, so pressure going up, it's going to have volume going down, so we have less space, so we want less particles. We're going to go towards the side with less moles. So that means we're going to increase our amount of reactants, but we're going to decrease our amount of products. Okay, so we're removing some of those gas particles, we're turning them into this aqueous solution and these oxygen molecules. So we're reducing the total amount of gas particles in our system there. Okay, the one we didn't look at is a temperature change, so let's just try one out. If this was an endothermic reaction, let's pretend it is. I'm not quite sure. I'd have to look this one up, but let's just say it's endothermic. So our heat, our kilojoules are on the left. If we removed heat, so say we put it in an ice bath. Okay, if we removed heat, think about which way it would shift. All right, hopefully you said towards the left to get that heat back, so we'd increase our amount of reactants and decrease our amount of products. So if we removed heat, we put this reaction in the ice bath, we'd go towards the left. If we added heat, it would force it the opposite way, towards the products. So hopefully this gave you a nice little overview of Le Chatelier's principle. Let me know if you have any questions.